Welcome to This Explainer. Today, we're diving into something absolutely brilliant. We're going to break down an elegant algorithm used for finding hidden strings. It's a classic computer science challenge, and the solution we'll be looking at today is honestly a masterclass in writing clean, efficient, and just really clever code.
Picture this. You've got the classic needle and haystack problem. You're staring at a massive jumble of random letters, and you need to know if a very specific word is hidden inside of it. But there's a major catch. You have to read the text strictly from left to right, and you are never, ever allowed to look backward. So how do you prove the hidden word is actually in there? Keep that strict constraint in your head as we go, because it's the absolute secret sauce to the entire approach we're exploring today.
Here is our roadmap for the explainer. We'll start with the subsequence check, jump into the two-pointer mechanic, trace the execution flow, handle those tricky edge cases, and finally, look at efficiency and key insights. All right, Section 1, the subsequence check. Let's define exactly what we are actually looking for here.
So, the highly technical term for our hidden string is a subsequence. Basically, a string, let's call it S1, is a subsequence of a bigger string, S2, if all of the characters from S1 show up in S2 in the exact same order. But, and this is a crucial but, they do not need to be consecutive. They can be completely spread out, separated by dozens of other totally random characters. Order is the absolute unbending rule here. As long as the sequence of letters marches forward, we've got a match.
Moving right along to Section 2, the two-pointer mechanic. Let's meet the two actors that make this whole thing work.
We're using what's called a classic two-pointer approach. Just imagine two fingers scanning across a page of a book. Our first pointer is I. It tracks our progress through S1, the needle we're hunting for. Now, pointer I is incredibly strict. It completely refuses to move forward unless it finds the exact character it's currently waiting for. Our second pointer is J. It tracks our progress through S2, the messy haystack. Contrast pointer I with pointer J for a second. Pointer J is relentless. It marches forward exactly one step at a time, scanning every single character of the haystack without skipping, no matter what.
You can really see how clearly this defines the relationship between the two strings. Pointer I acts like a strict gatekeeper. If we need an A, I just sits on A and waits. Meanwhile, J scans through the haystack. Is this an A? Nope, move forward. Is this one an A? Nope, move forward. The very moment J finds that A, I finally gets the green light to advance to the next needed character. This is the golden rule. J always advances, I never goes backward. And that guarantees our order is perfectly preserved.
And when you look at the core for loop in the code, it's remarkably compact. The condition there creates this beautiful built-in early exit. The code literally short-circuits the exact moment either string runs out of characters. If pointer I reaches the end of the needle, boom, we found the word, we can stop searching. If pointer J reaches the end of the haystack, well, we ran out of text to search, so we stop. There is absolutely zero wasted computing effort here.
Okay, Section 3, tracing the execution flow. Let's look at a concrete example to really make this click.
Let's set the stage for our trace. Say our needle, S1, is simply the string ABC. Easy enough. And our haystack, S2, is this jumbled mess right here, 2altrb53c.sse. We're going to scan S2 with pointer J and advance pointer I only when we hit our target letters.
All right, let's trace this out step by step. Pointer I starts at index 0, waiting patiently for an A. Pointer J starts at index 0 of the haystack, which is a 2, no match. So J moves to index 1. Oh look, it's an A, match. Pointer I is finally allowed to advance to index 1, and now it's looking for a B. Now watch J continue its relentless march. It checks L, T, R, still no matches. Pointer I is just waiting. Finally, at index 5, J hits B, match. Pointer I advances to 2, now hunting for a C. J keeps going. It hits 5, then 3, nothing. Then at index 8, J lands on C, match. Pointer I advances to 3. And check out what happens right here. The length of our needle, ABC, is 3. Since pointer I has hit 3, the loop terminates immediately. We don't even bother checking the rest of that haystack.
So once the loop exits, whether we found the word or just ran out of haystack, our entire final result check comes down to asking one beautifully simple question. Did pointer I make it all the way to the end? If I equals len in S1, it means every single character was found perfectly in order. We print 1 for success. If I is less than the length, it means it got stuck waiting for a letter it never found, and we print 0.
Which brings us to Section 4, handling edge cases. Because as we all know, things don't always go perfectly. Any robust algorithm needs to handle weird inputs gracefully.
First off, what if we search for nothing? What if S1 is a completely empty string? Well, the math here works out perfectly. Before the loop even begins, pointer I is sitting at 0. The length of S1 is 0, so I equals len of S1 evaluates to true instantly. The loop conditions are entirely bypassed, and it automatically counts as a success with exactly 0 iterations. It's an awesome little short circuit that aligns perfectly with computer science theory. An empty set is always a subset of every set.
These boundary conditions are managed so safely and so instantly. For instance, what if your needle is somehow longer than your haystack? Well, pointer J will simply exhaust the haystack before pointer I can ever finish its job. The loop just naturally exits. I is too small, and it prints 0. No out-of-bounds errors, no program crashes. It just works.
Now, here's a tricky one. What about characters that are out of order? Say we're looking for ABC, but our haystack is BT arc. That B appears first. But remember our golden rule? Pointer I refuses to look forward, and J refuses to look backward. Since I is stuck waiting for A, that out-of-order B simply passes by and gets completely ignored. Once A is finally found, pointer J has already moved way past that initial B. The out-of-order characters are implicitly rejected without requiring a single line of extra code. Finally, Section 5, Efficiency and Key Insights. Let's wrap up by looking at why this specific mechanic is so highly regarded by engineers, and look at its actual performance footprint. The crucial takeaway here is the sheer efficiency we achieve. Because pointer J never ever moves backwards, we scan the haystack exactly one time. That gives us a time complexity of big O of n, which is literally the absolute best-case scenario for searching a string. And what about space complexity? Well, we aren't building arrays, we aren't slicing up strings, we're literally just keeping track of two simple integers, I and j. That gives us an ultra-lightweight space complexity of big O of 1.
Let's quickly summarize the brilliance of this algorithm. It solves a complex problem using 2 pointers in a single pass. It enforces the strict rule of character order completely for free just by refusing to look backward. It saves precious computing power with an early exit condition. It seamlessly handles tricky edge cases like empty strings without needing messy if statements. And the entire logic boils down to a single true or false check at the very end.
This is an incredibly powerful tool to have in your programming tool belt. Once you really understand how these 2 pointers interact, one incredibly strict, one totally relentless, you can solve a massive variety of sorting and searching problems. So here is my challenge to you. Knowing what you know now, could you write this 2-pointer check in your favorite programming language today? Give it a shot. Thanks for joining me on this explainer, and keep building.